we're going to look at the relative stabilities of cycloalkanes. And ring strain. First, we want to talk about cyclopropane. Cyclopropane is a triangle. Cyclopropane is sp3 hybridized, and it has a bond angle that is about 60 degrees. The ring itself is planar. The carbon-hydrogen bonds are eclipsed, and with that 60 degrees, we have angle strain. And when we talk about angle strain, that is a deviation from the ideal angle. The next cyclic system we want to talk about is cyclobutane. If we draw it flat, we're looking at the box, but we have to give it a slight shape, and we're going to talk about why. Cyclobutane is also sp3 hybridized. It has an angle of about 88 degrees. The ring, which you're noticing, is not flat. It's not planar. And we're looking at the bent one, not the flat structure. You'll notice that it is slightly folded. The carbon-hydrogen bonds are eclipsed. And within that folded structure, we do have angle strain, which we said was the deviation from the ideal angle. Typically, if we are sp3 hybridized, our bond angle should be 109.5. But we're noticing with the cyclopropane and cyclobutane, we have a deviation from that angle. We want to also look at cyclopentane. If we draw it flat, that's the house. However, we are not going to draw it flat. What we notice as well with cyclopentane, it is sp3 hybridized. it has a bond angle of about 108 degrees. The carbon-hydrogen bonds are eclipsed. With the cyclopentane, you have little torsional strain. But we do, with that 108 degrees, have angle strain, which is a deviation from the ideal bond angle. When we talk about torsional strain, that's defined as the repulsive dispersion forces that cannot be relieved due to restricted conformation mobility. Lastly, we have cyclohexane. Its flat shape is in the structure of a hexagon, but remember, we don't utilize the flat shape. So here we have cyclohexane, which is sp3 hybridized. It has a bond angle of 109.5. So what we notice is that it is free of angle strain. As well as torsional strain. With the cyclohexane, the carbon-hydrogen bonds are staggered. And remember, we said previously, staggered leads to more stable. So the more stable ring out of a 3, 4, 5, and 6 member ring would be the cyclohexane. And that is because it is free of angle strain, it is free of torsional strain, and because the carbon-hydrogen bonds are staggered. We can, however, focus more attention on the cyclohexane, where we can look at a conformational analysis of that cyclohexane. So this conformation that you're seeing is known as the chair conformation. And the chair conformation is the most stable conformation. And because it is the most stable conformation, it is going to be lower in energy. So what we're going to do is just make a slight energy profile. And we're saying that the chair conformation is the most stable. So the chair is the most stable. The carbon-hydrogen bonds, they are staggered, and it is lower in energy. Other conformations of cyclohexane include the twist boat, the boat, and the half chair. The twist boat resembles what we have here drawn in green, so two boxes put together. And here would be where we would see the twist boat. They would be after the chair in terms of stability because they're also low in energy. The boat is shown here. The boat, in terms of energy, would come after the twist boat. So again, the chair is the most stable, and the twist boat would be after, then the boat, and then lastly, the half chair. Which is shown here. And a half chair would be the least stable. Because it is higher in energy. So you may be wondering how to draw the chair conformation. You can start with two horizontal lines, one closer to the left, and then we want to go down, and we want to do one kind of closer to the right. Then you want to point up, and then you want to point down. So let's try that again. One towards the left, one towards the right. Take the bottom, hit the top, take the top, hit the bottom. We're going to talk about how we're able to flip a ring. So we can also draw it to the right and then move a little over to the left. The top, hit the bottom, the bottom, hit the top. Let's do that again. Closer to the right, move it a little bit over to the left, top, hit the bottom, bottom, hit the top. So you can start with the horizontal lines and then add in your diagonal lines. Again, you can start with your horizontal lines and then add in your diagonal lines. With the chair conformation, we have different positions. So we can talk about equatorial positions and axial position. When we talk about equatorial, it is more of a diagonal line that we are going to see. And then when we talk about the axial position, we're going to see a straight line. Or if you want to call it vertical. So let's go ahead and draw our chair. And when we talk about equatorial, we said diagonal. So each carbon has one equatorial position. Each of these corners represents a carbon. So when we draw in our equatorial positions, we said they should be diagonal. So here, 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 or if we want to bring that one down, we can. Here, 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 here. So the red lines that we have signify the equatorial position. We can draw another chair so that we can see the axial position. Again, our carbons are represented by the vertices, the corners, the bends. And we said that axial was a straight line that's going to be vertical. It's going to either be up or down. So here, 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 and here. And each carbon has one axial position, which is signified by our green lines. So when we draw a chair conformation, we should be able to identify a position as either being equatorial or as being axial. With chair conformations, we can also look at cis versus trans. And these are going to correspond to disubstituted cycloalkanes, meaning that they can have two substituents. So let's look at a disubstituted chair. What we want to do, look at the carbons that are substituted. So that's signified with the blue dot. And we want to draw crosshairs. Or you can draw a horizontal line going through the carbons that are in the chair conformation. And we want to look at what are called limits. If we look at this methyl, you'll notice that it is above the red line. So we call this an upper limit. If you look at this methyl to the left, it is below the red line. So we call that a lower limit. Because they are opposite, one upper and one lower, this molecule, this disubstituted cycloalkane, would be considered trans because they are on opposite sides. One is upper, one is lower. Let's look at another example. I'm going to signify where my dye substitution occurs at those carbons. And through those carbons that are on the cyclohexane ring, I am going to draw a horizontal line. And I want to look at the position of my substituent. So here I have a methyl, and it is a lower limit. Here I have another substituent, and it is beneath the red line. It is also a lower limit. So what we notice is that our limits are the same. They are both lower. And if they are the same, then that means that the structure is cis. So far, I should be able to understand the stability of cycloalkanes and ring strain, and understanding that the cyclohexane is the more stable of the 3, 4, and 5 membered rings because it is free of angle and torsional strain. Its angle is closer to the ideal angle for an alkane, an sp3 hybridized molecule. The carbon-hydrogen bonds are staggered, which also leads to the stability of the cyclohexane. We want to draw the cyclohexane not flat in a hexagon, but we want to draw it in the chair conformation because the chair conformation shows the carbons and the hydrogens in a staggered position. If we did an energy profile on the different conformations of cyclohexanes that we can have, the chair was the most stable because it was lower in energy, followed by the twist boat, the boat, and then a half chair. And we learned how to draw chair conformations and looked at axial versus equatorial, and also understanding cis versus trans in looking at the limits of a disubstituted cycloalkane. Some things that we want to keep in mind when we talk about these cycloalkanes. We want our bulky groups to always be in the equatorial position. When we talk about bulky groups, we're talking about tert butyl. You typically see tert butyl as your bulky group. We always want a bulky group to be in the equatorial position because that position will be the most stable, and also because it relieves 1,3 diaxial interaction. So if the bulky group is in the equatorial position, you do not have to worry about a 1,3 diaxial interaction. So we're going to draw a chair conformation so that you all can see what is meant by that 1,3 diaxial interaction. So this is the diaxial interaction when the bulky group, or we'll just say the substituent in this case, is axial. When it's axial, we have 1,3 diaxial interaction. And that is what is shown in green. When a substituent can interact with those hydrogens. That are at that 3 position. The methyl would represent the 1 position. So in order to get to the more stable structure, we would essentially have to flip the ring. And when we flip the ring, my substituent is now equatorial. And we no longer have that 1,3 diaxial interaction. So whenever the bulky group is present, you want to put it into the equatorial position because that is going to be the structure that is favored. Again, that is going to always be the structure that is favored. So if we kind of want to summarize that a little bit, we can say that you want the cyclohexane in the chair conformation. And you want the maximum number of equatorial substituents. That's what's preferred. the maximum amount of equatorial substituents, in which we said we always want the bulky group to be equatorial. You always want the bulky group to be equatorial. Now the last thing that we want to look at are the three types of disubstituted cyclohexane. The first one we're going to start off with is the 1,2 disubstituted. With the 1,2 disubstituted, we can have our substituents in different positions. And that's what we want to look at. So I can have, and I'm going to use R to signify the substituent. What I can have is both groups axial, and this is my 1 and 2 position. If both groups are axial, that means that they are trans. I can look at both groups being equatorial. And if both groups are equatorial, that would still represent trans. Remember we talked about our upper and lower limits. And I told you guys to write in your horizontal line. And I can have one group that is axial and the other equatorial. And if I have one group axial and the other group equatorial, that would represent cis. So here are three ways that I can see a 1,2 disubstituted cyclohexane. Either with both groups being axial or both groups being trans. Both groups being axial or both groups being equatorial, in which they would be trans to each other. Or I can have one group axial and one group equatorial, in which they would be cis. With both groups being equatorial, this structure is the more stable. Remember we said the maximum number of substituents that are equatorial leads to the better structure. So with both groups equatorial, that again is the most stable. Please keep in mind that in doing a ring flip, an axial group will become equatorial and an equatorial group will become axial. So if we look at the following example, and I'll show you guys in a minute how to do a ring flip. That's an ugly chair. There we go. So if we look here, this position is axial. And when we put it here, once we flip the ring, we want to make it equatorial. This position here is equatorial. But when we flip it, we want it to be axial. So again, when we flip a ring, axial becomes equatorial and equatorial becomes axial. The second type that we want to look at is a 1,3 disubstituted position on the cyclohexane. So I'm going to give you 3 structures that we're going to look at. So here, showing our 1,3 position. And what you will notice, again, we can do our horizontal lines. So if both groups are axial, the structure is cis. If both groups are equatorial, the structure is also cis. But if one group is equatorial and one group is axial, then the structure is deemed trans. For the 1,3 disubstituted, the more stable is where we have one substituent always equatorial, and the other substituent axial. Which would lead this structure to be the more stable for the 1,3 disubstituted. The last type that we're going to look at is the 1,4 disubstituted. Here I'm going to draw 3 structures. In which we're going to see our 1 and 4 position, pretty much on opposite ends. We can have a structure in which both groups are axial. And if both groups are axial, this represents a trans molecule. We can have another chair in which both groups are equatorial. And if it's equatorial, then it is also deemed trans. We can have another in which one group is equatorial and the other group is axial. And this molecule would be considered cis. And remember, we're looking at our limits. And remember, we said the more equatorial groups you have, the more stable. So the diequatorial would be the more stable, and the diaxial would be the least stable. So again, those are the disubstituted positions that I can have. 1, 2, 1, 3, and 1, 4. Now we want to look at how to do ring flips. So let's just look at these chairs, or this particular chair. I can talk about the tips. Because this is up, I would call this an up tip. And because this one is down, I would call that a down tip. So you have the ability to start at whichever tip you would prefer. My preference is always the up tip. I like to start at the up tip. So let's just say I had a flat structure. And I wanted to take my hexagon and draw it into a chair conformation. When we do this, when you consider the dark wedge is always going to be up and equatorial. When you look at the dash wedge, that is always going to be considered down and axial. So what we want to do is draw our chair conformation as shown here. And we're going to mark off our carbons. And what I want to do is make sure that I number going counterclockwise. So CCW is counterclockwise. Try to put a little bit of white to break that up. So I want to make sure I number my cyclohexane in the chair conformation going counterclockwise. So I'm just going to start at the bottom and go counterclockwise in my numbering. So I'm going to call this one 1, 2, 3, 4, 5, 6. Now the numbering that I have here does not correspond to nomenclature. It does not correspond to nomenclature. So I have numbered my flat ring and my chair. I want to look at what I have at 1, which is an ethyl, and it's a dark wedge. So we said we want to put it in the equatorial position. So here up in that equatorial position. At position 3, I have OH. I want to also put that up and at an equatorial position. So I have that here. And then lastly, I have a chlorine. That's a light wedge. That's at position 5. So I want to put that down because it is a light wedge, so it's going to go axial. So again, I should be able to draw a hexagon into a chair conformation using these principles. So let's take our chair that we just drew. And what I am going to do is show you how we are going to flip this ring. So we numbered going counterclockwise, so we're going to start CCW, which is counterclockwise. We said this was 1, 2, 3, 4, 5, 6. And right here is an up tip. So I want to make sure my up tip, when I flip it, becomes a down tip. So you notice when I draw my other ring, I now have a down tip where the up tip was. And I keep my numbering the same. It was going counterclockwise. So that stays the same. You'll notice here, my ethyl is up. So when I draw it on my structure 1, I want to draw it up. But remember what we said. Here is axial, so here it becomes equatorial. I look at position 3, and my OH is up, and it's axial. So when I draw it again, I'm going to draw it at position 3, and it's going to be up, and it is going to also be equatorial. Because when we flip the ring, axial becomes equatorial, and equatorial becomes axial. And then lastly, I have my chlorine at position 5. And my chlorine is down and in the axial position. So when I draw it, I have to draw it down, and I have to put it in the equatorial position. And I need to switch this because I wrote them incorrectly here. So let's make that correction. We swapped our groups again. Our OH initially was in the equatorial position. So when we flip it, it goes axial. And then our ethyl was in that up position, and it is also equatorial. So it is going to go axial. I apologize. Make that correction. And this is how we do our ring flips. So you want to make sure you practice. So again, no matter where I flip the ring, for me, I started counterclockwise when I had my initial ring, and I started counterclockwise when I had my final ring. And I kept the positions of up and down.